Hi, sorry about that. For some reason, the iPad quit on me, and I had to, and the video exited, so I had to record a second video for this. I mean, this was supposed to be in one video, Green's theorem, and another video about flux, but now I have to do two videos about Green's theorem, and then the third about flux. But it's good that it stopped at the right time, which is for examples. For examples, let f of xy equal xyi plus x squared y cubed j. Calculate integral over c f dotted with t ds, where c is a triangle with vertices 0, 0, 1, 0, and 1, 2. So it's always very useful to draw a picture. This is C, this is 1, this is 0, sorry, this is 1. Let's say this is 2. And this is my curve C. So this is my curve C, and I want to calculate the line integral of my curve C. Now, first, I mean, there's two methods, yeah? I mean, you know the method that is 15.2, which is directly, which you are welcome to do and do it, and please do it so that it's practice. So practice, use the explicit method so that, I mean, you're used to it, which will tell you integral over C f dot t ds is equal integral over this side plus integral over this side plus integral over this side. Yes? And I will use Green's theorem, but in order to use Green's theorem, I have to go inside my rectangle. So let's call this T. So let T be the region enclosed by C. Now I have f is xyi plus x squared y cubed j. So m is equal xy and n equal x squared y cubed. This has continuous partial derivative for order 1 everywhere, yes, in R2. Then I can use Green's theorem. Then by Green's theorem, integral over C, which is anti-clockwise, of f, well, where C is a triangle with vertices oriented, well, with anti-clockwise orientation. So I have f dot t ds. This is equal integral over t, where here t is a triangle, of f dot t. So I have 2t here. It's not a very good notation, but anyway. So this is equal double integral. No, this is c. Sorry, I'm still here over c. So I rewrote it. Sorry. So this is double integral over t, which is a triangle. This is a triangle, or the interior of the triangle. See, is here, of nx minus my dA. But now I have m is xy. So what is m sub y? It's x. And I have n is x squared y cubed. So what is n sub x? It's 2x y cubed. Then this implies that integral over c of f dot t ds is equal double integral over the triangle of nx, which is 2xy cubed minus x dA. But now I have to choose, do I do dy dx or dx dy? Well, in this case both will work, so let's do dy dx. So how do I do dy dx? I draw a line parallel to the y-axis, and this will be equal. So I will do double integral 2xy cubed minus x dy dx. So it enters a region at the line at the x-axis, which is y equals 0, and it leaves the region at this line. Now this is x equal 1, y equal 2, so this line is y equal to x. So y equal to x, and my x is, I can move this line from 0 to 1. 0 to 1. And now I calculate the integrals. This is much shorter than the other way to parameterize each line. So this is 0 to 1. 0 to, well, let's integrate with respect to y. 0 to 1. What is the integral of 2xy cubed with respect to y? This will be xy4 over 2 minus xy, where y is between 0 and 2x. So it will be 0 to 1. Now y power 4, 16, 16 over 2, 8. So this will be 8x5, because here I have x4 and x5, minus xy, when y equal to x, so minus 2x squared, minus when y equals 0, this is 0. And this will be equal d here. Here I have dx, and this is dx. Now I integrate with respect to x. This will be 8 over 6 x6 plus 2 over 3 x cubed between 0 and 1. Notice that when x equals 0, this is 0. And here also I have this one minus, I plug in y equals 0, but you will get 0. So this will be 8 over 6 minus, not sure why this is transformed to plus, minus 8 over 6 minus 2 over 3, and this will be 4/3 minus 2/3, and this will be equal to 2/3, which is what you should get if you calculated explicitly. But you can see, I mean, you should appreciate here how shorter this method is. Now, example 2, calculate integral over c of x squared y dx minus y squared x dy, with c is x squared plus y squared equal x squared, anti-clockwise. I mean, this is anti-clockwise. You see the orientation? Anti-clockwise. So this is c. This is c, and this is a. I'm saying here a is positive. So how do I mean, one way to do it, parameterize r of t and do f r of t dot v of t. So in this case, m is x squared y, and n is y squared x. So I will use Green's theorem. So to use Green's theorem, I should go inside. So let D be the region enclosed by C. Okay. Now I have f is equal in this case what? X squared y minus x squared y and minus y squared x. So m is x squared y and n is minus y squared x. They both have continuous derivative of order 1 everywhere. Yes. So what is nx? Is minus y, is the derivative is minus y squared, and what is my? It's equal to x squared. Then by Green's theorem, the integral over c of x squared y minus dx minus y squared x dy, this is equal double integral over the disk of nx minus my, which is minus y squared minus x squared dA. I mean, you can, and now I have to calculate this integral, but I mean, since I have x squared plus y squared, and I have a disk, so this screens polar coordinate. So this is equal double integral of minus r squared, and dA is r dr d theta. Now my r is, I draw an arrow from the origin. This is r between 0 and a, and theta between 0 and 2 pi. So this will be integral from 0 to 2 pi, integral from 0 to a of minus r cubed d theta. And this is equal to 2 pi times minus r4 over 4 between 0 and a. And this is equal minus 2 pi a4 over 4, which is equal minus pi a4 over 2. And these are the two examples that I used to do in class. We used to do a little bit more advanced example in the recitation. So example. Now recall the field. I'm not sure I called it Vxy in previous. This is from 15.2. This field every time we're gonna use it. X squared plus y squared I plus x over x squared plus y squared j. Now if this is m, this is n, and we showed that the following. We showed that an x equal my, but the integral over c, which was in this case x squared plus y squared equal to 1 of f dotted dr equal minus 2 pi. Okay. Now you can show, and please do this, you can show that in fact the integral over x squared plus y squared equal a square of f dotted dr is also equal to minus 2 pi. You can, and here you cannot use Green's theorem. Why you cannot use Green's theorem? Because here I have a point which is at the origin where m and n are not even defined, so let alone its partial derivative. So we cannot apply Green's theorem in this case. So the only way to do it is to parameterize it, and in fact, no, here you can do it geometrically. So please review the example we did for x squared plus y squared equal to 1. And this is, you have, I mean, a big recommendation to do it for x squared plus y squared equal to a squared, do it geometrically by drawing the vector. Remember the vector were this way, which were tangent. Okay? So let's say this is A now, not 1. And I apologize for this. Yes, correct. This is fine. Now we cannot. So we cannot use Green's theorem since since m and n are not defined at the origin. Correct? But I need to use Green's theorem, I need f to be defined in the whole the region enclosed by the disk. Now let's ask a question. So question. Let K be a curve not containing, again, so this is against simply connectedness. You see, you have a hole inside your domain, so you cannot use a component test, and you cannot, I mean, even if the component test is satisfied, your field is not conservative. So even that my function is continuous the boundary, you still cannot use the Green's theorem. Let K, because Green's theorem would give you 0, because nx equal my, but everywhere except at the origin. Now let K be a curve not containing the origin, and R the region enclosed by K. So question A, suppose 0, 0 is not in K. Find integral, well, 0, 0 is not in R. Find integral over C of f dotted with the R. Well, what do I have here? I have a curve K like this, and not containing the origin in the region R. So what will be integral over C of f dot dr? But here I don't have problem in R, do you agree? So I can use Green's theorem, and I can use that my field is conservative. Because here my domain is like simply connected. I mean, my function n and m and their derivative are continuous in this whole domain that is simply connected. Or you can use also Green's theorem, and you have nx equal my, so this will be done integral over R of nx minus my dA. But I know that nx equal my everywhere, but at the origin is not defined, so here this will be equal to 0. Two things. I mean, you can do this without Green's theorem, so because you can say it's conservative and R is simply connected, so So by the root property equals 0. And you can use Green's theorem, but again, Green's theorem is just a general way, general form of the loop property. Now B, suppose 0, 0 is in R. Find integral over C of f dot dr. And here pay attention. So I cannot use Green's theorem here. Why? Because 0, 0 is inside R. And I have a set like this. Okay. How this is K and what is inside is R. How do I find my line integral in this case? So now I will go back to my construction with rectangles. Okay, I will use a similar idea. So do you agree that R contains x squared plus y squared, where the disk here, this is the origin, okay? I'm telling you here I have trouble at the origin. Why I have trouble at the origin? Because n and m are not defined, so I'm not using Green's theorem. So R contains x squared, the disk s squared plus y squared smaller than a squared for a small enough. The origin is inside R, so I can draw a circle here. So let's do this with a different color. And this is A. Okay. Without the arrow. At this point. Okay. Now let CA be the disk, will be the circle x squared plus y squared equal a squared counter clockwise. Okay. So now I'm given that this is CA. Now what I will do is the following. I want to avoid this center. So what I will do, I will divide my region into two pieces. And now I will do this in blue. Let's divide my region into this region. I go up, go down. Okay. And into the following region. And I go here and then I go down. So this is this region. Sorry. So I'm aligning K, but now I go this way and then I go this way. And then I go down, and then I go this way. Okay. Now notice that the integral over the blue thing, okay, plus, so the integral may be just blue. So the integral over blue curve plus the integral over the green curve, not Green's theorem, it's green, the color green, is equal to what? Let's see, if I go to the blue one, I do this one here. Remember, this is the blue direction. And then when I go to the green, I do, yes, when I go to the green, I do this. This is the green thing. I go down and I go this way. Now notice that on the line segment, I have blue and green opposite direction, so the line integral of the vector field will cancel. And here I have opposite direction, so the blue and green will cancel. So what do I still have? I still have K, the boundary, and I still have the disk or the circle, but in the opposite direction. See the blue and the red thing and the green thing, it retraces the circle in the opposite direction. So do you agree that if you follow the arrow, this will be equal integral over k plus integral over minus CA. So this is f dot t ds, f dot t ds. I gave another example like this, by the way, in the problem set, and it's written short, and it's also in the book at the end of the section of Green's theorem. Okay, I mean the book use a different approach. I recommend this approach. So I have k. Why? Because when you follow the arrow in the green and you follow the arrow of the blue curve and the arrow of the green curve, you have you retrace the whole boundary k, but you also retrace the disk, but in the opposite orientation. So it's minus CA. Now, and this will be, so, and now what is the integral over the blue curve? Now we can use Green's theorem here. Do you agree? Because m and n have continuous partial derivative here because we are away from the origin. So this is equal to 0 because here I have nx equal my. And here I have nx equal my. So the integral also over the green curve is equal to 0. And this is equal integral over k f dot t ds minus integral over ca f dot t ds. And we calculate integral over ca. This is the integral over ca is always equal to minus 2 pi. So this gives me that integral over k of f dot t ds is equal to integral over ca f dot t ds equal minus 2 pi. And this is for all curve k. I didn't need a parameterization. It doesn't matter what is my k in this case. Okay? Can be just, it can be something like this. Okay? I don't need to parameterize. I always get minus 2 pi. Okay? I will stop this video now, and then in the next video I will explain the flux into dimension and give the second version of Green's theorem.